How can you use one of these to tell how far away a galaxy is? Well, if you ever bought an LED torch when they first appeared around about 2005, you might remember how the adverts used to try and make them sound extra exciting by saying that it was 1,000,000 candle power. And what that means is that a torch has an equivalent brightness to 1,000,000 standard candles. And a standard candle is a candle of known size and known material burning at standard atmospheric pressure and standard room temperature. It's basically a way to have a standard unit of brightness that helps people to conceptualize how bright a light source is. Realistically though, it's a bit daft. You simply can't visualize what 1,000,000 candles would look like, let alone how bright it would be if it was all squished down into the same area as the head of a torch. So now we talk about lux and lumens instead, and it's a bit more practical. But there's something else you can do with the standard candle. You can measure distance. If you know the exact brightness of a candle, and you measure its brightness from your perspective, then by doing a bit of maths, you can work out how far away it is by how much less bright it is at the point of observation. This is, of course, incredibly impractical and inaccurate on Earth, because you have to account for things like the atmosphere and how much it adds to the dimming of the candle because of dust and moisture in the air, refraction, and more likely, candle gets blown out. So it's useless, right? Well, no, you see, if the distance you want to measure is in a vacuum, it becomes a lot simpler. So you could use this method to measure something like the distance of another galaxy from us. But there's two problems with that. Firstly, you need to get a candle to the place you want to measure the distance to. And secondly, given it's probably hundreds of light years away, you're going to need a bigger candle. The solution, it turns out, is to use the brightest lights in the universe, which is supernovae. You see, when a star is born, it starts out by fusing hydrogen into helium, and then as the hydrogen runs low, it starts fusing the helium into carbon, and so on, creating heavier and heavier elements until it gets to silicon, and it starts fusing that into iron. And this is where a crucial stage happens, and the process of fusion now starts using more energy than it creates. You see, up until now, the mass of the star is being held in balance between the gravity trying to squish it down and the fusion energy inside it forcing the matter back outwards again. But now that balance has been lost and gravity makes the star collapse. Once this happens, and if the overall mass of the star is big enough, it'll collapse down in on itself, and this sudden increase in heat and pressure super boosts the fusion process, and in an instant it flips and the pressure becomes more than the gravity can hold it together, and it blasts out into space, releasing masses of matter and energy into the universe. And this is also where a lot of the heavier elements get created. But there's also a specific situation that can trigger supernovas known as type 1a supernovas, and this is where you have a white dwarf. Now, a white dwarf is if a red giant isn't big enough, it'll collapse in on itself, but it'll become a white dwarf and not go supernova. In order for it to go supernova, it needs just enough matter, about 1.4-ish times the mass of our sun, to create that situation. Now, a lot of systems have binary systems where you'll have a white dwarf sharing its system with a red star. And what happens is, when that red star gets to the end of its life and it starts to expand, it expands to the point where the outer mass of that star falls into the gravity well of the white dwarf, and the white dwarf starts leaching that matter. And as soon as that white dwarf's leached enough matter that it now weighs 1.44 solar masses, it goes supernova. So it happens at a very specific size. And the thing that makes them so valuable is, as a measurement tool, they're fairly common, so we can measure multiple in the same galaxy to check our calculations. And when they go supernova, their mass is very specific, so their brightness is very predictable. And they have a very specific spectral image as well because of the elements they create, so we know when we're looking at one. And from this, we can measure their luminosity and then calculate how far away they are based on how much they've dimmed over distance. Because it's in a vacuum, there's nothing to get in the way and add extra dimming. And that's why these type 1a supernovae are known as standard candles, and it's how we measure the distance to distant galaxies.